This is the record for the class number 13. So this class we are going to solve the planar frame problem, and the figures that you are seeing now is an illustration of the frame that comprise 4 structural members. You can see that the member here is connected to the horizontal members at the node number 2. The flexural rigidities of all members are prescribed over here. The length, the dimensions are all given. The boundary condition at the node number 1 is the fixed support. So this support restrain this node against the translation in x, y, and rotation, whereas another support, number 5, is restraining this node against the vertical movement and rotation. But the x displacement is allowed. Anyhow, the x displacement is resisted by the translational spring, of which the stiffness is 200 EI over L cube. The node number 4 exhibit the hinge that transfer only the shear force, but the bending moment will not be carried over this hinge. We have the point moment applied at the node number 3 and the point force applied at the node number 4. We have uniformly distributed load over this horizontal member, and we have the sort of suction force acting on this inclined member. Then we set up the degree of freedom for the formulation of this problem. We start with the node number 1. Degree of freedom start from U1 in horizontal axis first along the x, U2 along the y, and U3 is a rotation. This member is called member number 1. And then the node number 2 we have the 4, 5, 6. Number 3 we have 7, 8, 9, and number 4. Number 4, first of all, we think about the part, the degree of freedom that belongs to member number 3. So it is 10, 11, 12. And then at this node number 4, but the part that is attached to member number 4, you have the degree of freedom U10, U11, and U13, because the 12 is for member number 3, and then 14, 15, 16. Now, I will show you 2 approaches to solve this problem. So I name it in calculation number 1 and calculation number 2. For the calculation number 1, I will carry out the coordinate transformation by hand, literally. So it is carry out in the way that is friendly for manual calculation. Whereas the calculation number 2, I will follow the procedures that is universal for the computer structural analysis. That means it is more friendly to the computer programming point of view. Anyway, both of these will lead us to exactly the same solution. So we will take a look at the solution by these 2 approaches one at a time. But we have one assumption. In general, it is always the case that the axial stiffness of the members are generally much larger than the bending stiffness, and the axial deformation is more or less negligible in comparison with the flexural deformation. So we will use the concept of the axially rigid member, and we will just cut some of degree of freedom out of our consideration in the formulation of the problem. So let us start with the first one. So the first one, calculation one, here I came to this spreadsheet. In order to make the stiffness matrix, well, if you look at this problem, you can see that the member number 1, number 2, number 3, they are aligned with the y-axis and the x-axis. That means the degree of freedom in local coordinates, the transverse degree of freedom for the beam, is actually aligned with either x or y. That means we can set up the stiffness matrix without the use of coordinate transformation. Anyway, we have to set up the starting node and the ending node in the way that help facilitate that operation. So we look at this one here. For the member number 1, I will set up the first or the starting node being the node number 2, and then ending node at number 1, and that is going to make the local coordinates C pointing towards the bottom like this. So I put here number 2 and number 1. In fact, the alpha or the orientations which is referred to the x-axis is minus 90 degrees. But actually we don't make use of it over here because the transformation of the matrix is mainly carried out by hand. So let's take a look at this. I have the reason to set this point number 2 as a starting node, because if it goes like this, you will see the transverse degree of freedom goes, they go to the right hand side, which is along the x-axis. So if I come up with the element stiffness matrix for this beam or this frame member in the local coordinate, I can just make use of it directly and plug it into the global coordinate setup. So you will see in the following. Over here, you can see that the first one, the first DOF is aligned with U4. The second one, the rotation is with the U6. You can look at this, right? You can see U4 and then U6. U5 will not be included over here because we are going to say that it is stiff. So we don't really have to talk anything about U5 because U5 is got to be 0. And then U1, which is over here, and U3. So I put all these global coordinate degree of freedom at all these points. So this is the number 1 for local, number 2 DOF for local, number 3 DOF, and number 4 DOF. And then I'll be computing the stiffness matrix of this beam member. So first of all, it is 12 times EI over L cubed, and that is going to be the same over here, and this one here, and this one 12 EI. Next one is equals to 6 times EI over L square, and then this is equals to 6, this is equals to 6, this is equals to minus right? This is equals to this minus this is equals to this, and this is equals to this one. Okay, and here is 4 times EI over L. This is 2 times EI over L. This is 2EI over L, and this is 4EI over L. Okay, and then we'll be migrating all of these into the matrix size, a matrix of which the size is exactly the same as the system matrix. So we have 4, 6, 1, 3. 1 and 3 are not included in here because U1, U2, U3 are 0. U5 is also 0. U15 and U16 are 0. So all these 0 candidates are not included in this place. So U4, U6, and then here. Okay, the rest of this, well, you have nothing to do with because your extent is covering just F4, F6. Okay, nothing about U1 and U3 in here. Sorry, zero this up first. Okay, then we move forward to element number 2. For element number 2, we have to set up the starting node being this one here, and ending node is this one here, which is the number 3 and number 2, because we named this node number 3 and this node number 2. So the local coordinates C is pointing towards the right. What is good about this, having C pointing towards the right? Well, first of all, it's pointing towards the X direction, and that makes your transverse degree of freedom 1, 2, 3, 4 align with the y-axis. So it is pointing upward to the positive y direction. And then we put in F number 8, F9, F5 and F6, U8, U9, U5 and U6. Okay, I will copy this from here, and then I check. Okay, everything seems to be perfect. Okay. All right, looks good. And this, your alpha is actually 0, but anyway, this is not used in here in this calculation. The EA was said to be a large number, so it is huge compared with the bending rigidity, but anyway, we are not using this EA in this calculation because we be saying that, okay, the degree of freedom number 4, number 7 and number 10, which are along these beam members, they cannot stretch or compress. So U7 is identical to U4 and U10. So I will keep only just U4 in the formulation here. I will not put the U7 and U10 in the formulation, so you will not see these two variables as they are the same as U4. Then, okay, zero this point out first. Then we will plug this into the matrix. So the row for F8 and equation for F8 and F9. And then we have the column that associated with the U8 and U9. So I have this here, here, and here. Okay. Then the next one, U5 and U6. We don't have U5, so it's not there, but I have U6. So U6, F8, right? Row F8 and U6. So I just put in there. I just copy it down there. Okay. What is the next? F5. There is no F5, so don't forget about it. And then F6. F6 is this one. So first of all, F6, U6, and then F8, F6, U8, and F6, U9. So I'll will put these in boldface. And you can see, okay. Next, element number 3. For element number 3, this node is the node number 2, and this node number 4. So starting node is number 2, ending node is number 4, and the orientation is 0. The C points towards the right, positive X direction, and the global degree of freedom that are in line with the local ones are listed over here, these 4. So U5 is in line with the lowercase u1, U6 is with lowercase u2, U11 with the lowercase u3, and U12 with lowercase u4. So U5, U6, U11, and U12, and we have F5, F6, F11, and F12. And I will plug in, forget about F5, U5, I have U6, I have U11, and I have U12. Okay, I will copy the matrix down to here. Okay, so only this group 6, 11, and 12. Start with 6, 11, and 12. Okay, F11 and F12, and this okay, now you see all oops, what happened? Okay, element number 4, starting node number 4, ending node number 5, it points toward that direction. 4, 5. Now the angle is measured at the starting node in the reference is with the x-axis, so you can open the angle like this from the x, okay, go counterclockwise like this, or if you go clockwise like this, you got to put the negative sign. So it is the minus arctangent of 4/3. If you know that the height ratio to this horizontal ratio is actually the 4:3. Okay, so you can use the arctangent to find this angle. And now we have to set up the stiffness matrix in local coordinate. So in local coordinate, you have the F1 to F6. This one is an inclined member, so we have to include the axial stiffness there. We cannot just drop it off. Okay, so U1 is along this. Sorry, I didn't put it there. Sorry, this has to be adjusted. U2, this is U3, this is U4. Oh no, not U4, U5. This is U6. And basically, if we want to include the U1, okay, so here is your U1 and this is the U4. Okay, we have this, and then the direction cosine was set up. So the direction cosine is made of the cosine and sine and minus sine and cosine, and this is 1 and this is equals to this, and I'll be copying it down. Okay, all right, so the direction cosine is established, and then we can set up the element stiffness matrix in the global coordinate. So we take a look at this one here. In global coordinate, this member is made of U10, U11, U13, 10, 11, 13, and 14, 15, 16. All right. So F10, 11, 13, and 14, 15, 16. U10, U11, U13, 14, 15, 16. F10, it should be the uppercase because we are talking about the global coordinates. Now I'll be making the matrix which is transform already. So this is the MMULT of transpose of what? Transpose of the direction cosine, and then we multiply it with MMULT of this stiffness matrix and this direction cosine without transpose. There you go. We get this. Now we will bring this matrix into the matrix size, this blank matrix of which the size is the same as system matrix. So we have U10. Basically the U10 is actually U4, right? Horizontal displacement. I just mentioned before that U7, U4, and U10 are identical, so we're gonna keep only U4 and make U7 be U4 and U10 be U4. So okay, F4, 11 and 13. So we can put it in here, F4, U4, and then U11. You have nothing to do with 12, and you have something with 13 rotation and 14 as a displacement. Next one will be 11 for F11, 11 with U4, 11 with 11, 11 with 13, and 11 with 14. Nothing to do with 12, so you have 13 and 14. 13, U4, and you have 14 also, right? So this one, okay. This one is equal to 13 and 11. 13, 11 and 14, 11 is gonna be there. And here 13, 13. Okay. Yeah, let me put them in boldface. Now we are done with the element stiffness matrices. We will combine all of them into the system of equation. System of equilibrium equation. We'll copy this, paste it there. Okay. We'll zero everything out. Okay. This is equals to this plus this plus this plus this, and that's it. I'll copy this through, and remember that the last element here, we have the spring of which the stiffness is 200. So I need to add the 200 in there. Okay. Right. We have now the contribution from the stiffness spring. They're all in there. Let's take a look at the force vector. So here we are going to compute the force vector for this problem manually. That means I'm not doing anything with the transformation matrix for the vertical and horizontal members. But for the inclined members, still we have to use the direction cosine. So let's take a look. The member number 1 is subjected to these point forces pointing towards the left hand side, and you can see in blue and in gray. So this blue force cause these fixed end reactions. The fixed end reaction is resisting this blue force, so it points towards the right hand side in the opposite direction to the blue force. The component of these yellow forces are given in here. You can check. This is like PB squared times 3A plus B divided by L cubed. Alright, so the blue is associated with this blue, the gray is associated with this gray. Likewise for here, blue is from here and gray is the contribution from this one here. Blue is from here, gray is from here. So I computed and I added up the effects from the blue and the gray we have the fixed end reaction pointing towards the right hand side. Both of them have the magnitude of 10, whereas the moments that is resisting these two forces to keep this in equilibrium is 18.75 and 18.75. So you know that this is associated with degree of freedom or with the equation for the F4. Alright, so 10 is to the right and F1, 10 is to the right, but we don't have F1 here, so we just put the 10 for F4, and then the U6 is 18.75 positive, it is counterclockwise, and the U3 is negative 7. U3 is negative, so we go with the with F6, which is 18.75, and for this one U3 F3, you don't have them in the equilibrium equation because it is at the support, so we take them out and we highlight over here both face. Done with the force vector for A. Then let's look at the force vector for the member number 2. So member number 2 is subjected to this uniformly distributed load over this region. The span is 3 meter, 3L, and the magnitude is 3 EI/L cubed. So according to that uniformly distributed load pointing outward, then we need the reactions to be going upward, of which the magnitude is 4.5. This is associated with degree of freedom number 5, which is not listed over here, so we don't care. We have the U8 being 4.5. We have the U9, which is going in the counterclockwise direction, which is 2.25, and the U6, which is minus 2.25. So we don't do anything with the direction cosine. We don't use the direction cosine over here, as it is convenient enough for us to come up with the force vector without the transformation, because you can align the local coordinate with the global coordinates. Let's say local degree of freedom with the global degree of freedom. Okay, we are done. We come over here to the next member. The next member, we have these reactions to this uniformly distributed load over this region. So you calculate it, you get the vertical upward forces and moments like this. F5, it's not listed here. You have the F6 being this one, right, which is 9. Number 8 is not there. Okay, we have 11. 11 is 9 upward, and 12 is minus 9 because it is clockwise. I both face it up and let's check. Okay, it is in the same lines as before as the stiffness, so it looks good. Now for this one, I have to, first of all, you can look at this member here. The setup is in local coordinate. Okay, we can come up with the fixed end reactions. 1, 2, 3, 4, 5, 6. I put it this way first. So the first one is associated with the degree of freedom number 1, but along with this F1 direction, you don't have anything. The distributed force is not having any component going in this direction, so U1 and 1 and 4 will remain 0. Now this is your local coordinate, your local degree of freedom setup, and you find that your reaction is pointing in the opposite direction to this setup. So you will have the negative number. So what is the magnitude? You have the 4 multiplied by 10 divided by 2, you get minus 20, and here is also minus 20. Regarding the moment, you have the 4 multiplied by 10 square over 12, but here is the clockwise, so 4 times 10 square over 12. Okay, and the other one is negative of this one. Then I will copy this to here. The thing is that F1, this is associated with, this is constructed in local coordinates. So okay, that means it has to be transformed into the global coordinate, and in order to do that, we will just make this equal to MMULT, matrix multiplication of transpose of the direction cosine multiplied by the force, and close it down, and there you go. You get these force vectors, which is associated with this, or actually it is U4, right? F4, F11, F13, F14, 15, 16. Then after the transformation from your local coordinate 1, 2, 3, 4, 5, 6 turns out to be this. I will copy this and put it here to explain what is inside this. Next step, all of these, well, we have to just put this okay. All right, F4, F11, F13, and F14. For 11, 13, 14, 15, 16 is not included. And we will combine the fixed end reaction from all members, so that makes this one plus this one plus this one plus this one. Enter, and I'll copy it down. Okay, we have the external force vector, which is the contribution from. Now we will consider the external force, which is from, well, they are from this point here, the applied moment at the node number 3, and the applied vertical force in the downward direction at the node number 4. So these are the degree of freedom number 9 and number 11. Number 9 it is positive as it is counterclockwise. This is negative as it goes downwards, which is opposite to the positive y direction. So number 9 was 15, and here is number 11, it is minus 20. So at this point here, we will make the known vector being the external force minus the fixed end reaction, and it turns out to be this vector. So we can find the displacement solution by taking multiplication of inverse of the stiffness matrix multiplied by this. There you go, we get it. Keep in mind that the U4 is actually equal to U10 and U7. So this is U10 and U7 and U10. Okay. So we are done with the first approach. The procedures that is very friendly for the hand calculation. We did many things. We cast the stiffness matrix for elements that are aligned with the global coordinates by hands. We didn't use the direction cosine for the transformation because we align the local coordinate and make sure that the DOF we have aligned with the global degree of freedom. So that is good for hand calculation. But now we'll be moving into the approach which is generally good for the computer programming point of view. So we will set up the stiffness matrix of the whole system again, but we will be doing all of these procedures in a different way, as I will show you here. So first of all, let's look at it together. We have element number 1, which is this one here. Over here, I will set up the starting node being the node number 1 and ending node being the node number 2, which is different from the case we had before. The reason why I do this because that's gonna make my element stiffness matrix, the order of the row and the column will goes like U1, U2, U3, U4, U5, U6, which is quite easy for me to plug in. Well, if you write the computer program, it doesn't bother us anyway because the computer will just do the plugging in automatically, so it doesn't need any of your effort. But anyway, we can try it in a different way from the problem, from the approach we did before. So as we use this as the starting node and this is the ending node, that makes the local coordinate pointing towards the positive y direction like this. Now you can see the C going up. If the C is going up like this, and then you rotate your head in a counterclockwise direction by 90 degrees, you will find that the transverse degree of freedoms are pointing towards the negative x direction. It doesn't bother us anyway. So starting node is here, the x-axis is horizontal axis like this. So we find the angle by opening it up in a counterclockwise direction like this. Okay, open from this up to here. That makes the 90 degree, right? So that is equals to 0.5 times pi, that is the 90 degree. Okay, then now you look at the element stiffness matrix. The element stiffness matrix includes everything from the axial deformation along the C is the U1 F1. This is for U2 F2, U3 F3, U4 F4, U5 F5, and U6 F6. Okay, so these represent the global DOF and global equilibrium equations. Oh, sorry, local coordinates. Sorry. And then we need this direction cosine. And the next step, we will come up with the element stiffness matrix in global coordinates. So that is equal to matrix multiplication of transpose of the direction cosine multiplied by the multiplication of the stiffness matrix and the direction cosine. Here, close the bracket. Okay, I get this. And then we see that this is for the degree of freedom okay, row wise is the equation for F1 to F6, and column corresponds to the displacement in global coordinate U1 to U6. So we will bring all of these into the matrix, of which the size is identical to the system of equations that you will have at the end. And you see that you only have U4, U5, U6, F4, F5, F6. You don't have 1, 2, 3. So basically, these 9 entries are relevant to our consideration. We take out 1, 2, and 3 by row and column elimination. You can keep them. You can use Lagrange multiplier. You can compare the solution. You will be getting exactly the same solution. And okay, I will finish up the stiffness matrix first. Move now to the element number 2. Element number 2. This node is the node number 2, and this is node number 3. So previously, we used the starting node as number 3 and points to the number 2. But in here, I think maybe it is easier to keep it 2 and 3. So the order of the degree of freedom starts from 4, 5, 6 and followed by 7, 8, 9. So we don't switch around the order. So I'm gonna make it 2 starting node and 3 as an ending node. And that makes the alpha angle. So as this is a starting node, x-axis is here. So we open up the angle, and then that makes you 1 pi or 180 degree. So we put the pi in there. Again, these are, well, I just copy and paste here. So I set up the element stiffness matrix in local coordinate first. The angle is prescribed over here. So I will come up with transpose of the direction cosine multiplied by the matrix multiplication of the stiffness matrix in local coordinate multiplied by direction cosine another time, and there you go, we get the transform stiffness matrix. So let's take a look. As the starting node is number 2 and ending node is number 3, so the order of the degree of freedom is 4, 5, 6, 7, 8, 9. F4 and U4, sorry, I need the uppercase F. Okay, 4, 5, 6, 7, 8, 9. Unlike the case before that you have the 8, 9, 5, 6, because the order of the starting node turns out to be the number 3 and the ending node is number 2. Okay, so it's switched around, but no matter how you switch them around, as long as you are consistent with the overall procedures, you calculate the force vector in the consistent manner and so on and so forth, you'll be getting exactly the same solution. So it doesn't really matter. Now 4, 5, 6, 7, 8, 9, 4, 5, 6, 7, 8, 9, we have all of them. Then we will just take this in here. Get it? Alright. Move forward to element number 3. Element number 3 is here, and starting node is number 2 and ending node is number 4. So I like this order better. Well, computer like all, but I just like it because this is the sort of the hybrid between the computer structural analysis and manual calculation, because I still have to plug in these entries from the element stiffness matrix. So I just choose the convenient way, having the order going like 4, 5, 6 and then 10, 11, 12, rather than having 10, 11, 12 and 4, 5, 6. Okay, so the number 3 will have 2 to 4. 2 to 4, the local coordinate points towards the right hand side, and that makes a 0 degree angle for the alpha. So this is 2 and this is 4. Again, F1, U1, local coordinate, degree of freedom, and forces in local coordinate, and that is going to make us the transpose of this multiplied by this, and so what are these rows and these columns association? So 4, 5, 6, 10, 11, 12, 13 has nothing to do with element number 3. Okay, 4 uppercase because we are talking about global. F 10, 11, 12, right? 10, 11, 12. Okay, so U4, U5, U6, and then U10, U11, U12. So I drop in from here 4, 5, 6, 4, 5, 6, and then 10, 11, 12, come to 10, 11, 12, and last is this 10, 10. Okay, I put the boldface for these entries such that it is easier for you to spot these entries. Now, element number 4. We move forward to element number 4, and we have, I'm gonna set up the starting node being the number 4 to number 5. Number 4 involves the degree of freedom 10, 11, 13. Okay, so let me put this 4 and 5. So the alpha angle, if this is the x-axis, this is a starting node, so you can measure the angle by open it in the counterclockwise direction, or if you come to the clockwise direction like this, you're gonna have the negative sign. So this angle is actually the negative, the minus of arctangent. You know, these dimensions is 8L and this is the 6L dimension, and you want this angle, so your arctangent is the ratio from this side to this side, so that's the ratio of 8 to 6. Oh, that is 4 divided by 3. Again, we set this up in local coordinates, and then we get our local forces and local equilibrium equations, and we can establish the relationships, the stiffness matrix in global coordinates in the following. Okay. So in global coordinates, you have this degree of freedom set up F10, F11, and F13, and F14. Okay, 15, 16. This is U10, U11, U11, U13, 14, 15, 16. And we have U10, 11, 13, 14, 10, 11, 13, 14 in here, alright? 10, 11, 13, 14, you don't have 15, 16. So these are, let's see, 10, 10. Okay, 10, 11, and it goes like this. Here is 13. This and the last one. Now we can set up the global system, well, the system of equation system of equilibrium equation. And that is equal to this plus this plus this plus last one, this from the element number 1, and then I just copy only this one. We have to add 200 in there in order to incorporate this translational spring into the overall stiffness. So we move next to the force vector, the fixed end reaction first. So we come back to element number 1. As the element number 1 looks like this, the setup of the local coordinates is like this. That makes those transverse degree of freedom going backward to the minus x. Now we look at the force vector. You can see that the force vector we come up with as the effect from these two forces. We have it going to the right and these two. And that means when you put these force vectors, when you establish the array for the fixed end reaction, you need to address the sign that you have from the local coordinates before. And let me move things around a little bit. So in local coordinate, you're gonna have F1, 2, 3, 4, 5, 6. So start with the first one. So first one, well, now we look at the first node. The first node here, we don't have any force in the axial direction, so the number 1 and the number 4 will be 0. Then 1 and 4 0, so next one is this, which is the F2. F2 is actually pointing towards the right, so that's gonna make the minus 10 in the fixed end reaction vector. Number 3 is this clockwise direction moment, and it is on the opposite side from the counterclockwise. So it is 18.75 minus 18.75. Number 4 is 0. For number 5, it points toward the right, so it is minus 10. And the last one is the counterclockwise direction, so we get this. Next, we will perform the transformation. F1 F until F6, actually we have all of them, they correspond to this equation. Okay, just accidentally you have F1, F2, F3, F4, F5, F6 just the same, but you will see In the other case, that you don't necessarily have the same F1, 2, 3. This is just the setup in local coordinate, and this is the setup in global coordinate. So I call it FER in local coordinates. FER in global coordinates. The right hand side one is the setup in the system matrix, but it is still the fixed reaction in global coordinates, but in the different setup in the different array size. This one is equals to matrix multiplication of transpose of this, this, close the bracket, comma, if we are in local coordinates, Control Shift Enter. Okay, so you can see the minor change from here to this point here, because the F2 of this element, one is the axial direction, 2 is here in this transverse direction, but the transverse direction in local coordinate seems to be the x direction in global coordinate, and the x direction corresponds to the F1, right? So you can see that F2 in here just come to F1 in there, and as your fixed end reaction points toward the positive x of the magnitude 10, you can see that once it is transformed into the global coordinate, it turns out to be plus 10. The moment still the same. Another one, the F4 is turn out to be the plus 10 as well, and like this. Then we select the entries that are relevant in this global the system of equation setup, and the 4, 5, 6 are here. Alright, 1, 2, 3 are not included. We are going to do the same thing for this one. Let me see. Okay, so for element number 2, look at these together. Element number 2, as you set up the degree, the local coordinate this way, local DOF goes this way, but the point is that the member number 2 is subjected to this uniformly distributed load, and the fixed end reactions to this downward distributed load, you will have the vertical upward reactions, of which the magnitude is the W intensity multiplied by 3L divided by 2. You end up with 4.5 and 4.5 upward. However, this 4.5 upward seems to upset this setup because the degree of freedom, the displacement, is pointing downward in the positive sense in local coordinates setup. So we will plug in and then we will address this sign convention. So start with the first node here. The first node here, you don't have any axial direction, the force in axial direction, so it is 0 for the lowercase f1. The lowercase f2, which should be going downward, but you have the upward 4.5. Okay, so right, okay, I just zero things out first. Okay, so f1 and f4 is going to be 0, F2 is minus 9, minus 4.5. Minus 4.5. How about this? The moment, it should be the counterclockwise, right? But you get the clockwise, so 2.25 will be negative. And I record the minus 2.25 in there. Number 4 is 0. Force number 5 minus 4.5 as it is in the same direction as F2. And then for the moment, 2.25. So everything we have in the local force vector is transformed into the global fixed and force reaction vector, and we have the corresponding degree of freedom like this. So for local degree of freedom, it is for the equation F4, F5, F6, 7, 8, 9. And you have 4, 5, 6, 7, 8, 9. So, okay. 4, 5, 6, 7, 8, 9. Alright, done. Let's move forward to the next element, number 3. Starting node here, ending node there. So the setup is like this. The C axis points toward the right. Positive displacement and force are going upward. I compute the corresponding reaction forces and moments. I get 9, 9, 9, 9. Alright. Luckily, this case, it is going up and this is going up as well. So it is quite easy for us to drop in. But first of all, let me put in the degree of freedom. So this is U5, right? U6, U11, and U12. And then I copy this and drop it here. I zero everything up first. Good. So U5, you plug in the corresponding to equation for equilibrium in this U5 or direction of the F5. Okay, we plug in the 9. U6, we plug in the 9 as well because this is going along. 11, we plug in the 9, and 12, we plug in the minus 9. So 5, 6, 11, 12. Uh, 9, 9, 9, and minus 9. Okay. Four, 5, 6. And then we have the 10, 11, 12. 4, 5, 6, 10, 11, 12. Okay. Element number 4. We have this setup of local degree of freedom. This is your force distributed load. This is the corresponding reactions. So the degree of freedom number 1 and degree of freedom number 4, we have nothing, they will remain 0. This is going downward, but your positive setup of DOF is going upward like this. Then we know that this is going to get the negative sign there in the matrix, in the vector. Okay, so we start with the magnitude of this one, which is equals to, I think it is 4EI or L cube, multiply by 10, divide by 2, you get 20. The same thing for this one here. For the moment, it is a 4 multiplied by 10 multiplied by 10, which is actually 100 over 12. This is the magnitude. We will address the sign in the vector. So this is a DOF2, DOF3, DOF5, DOF6, 1 and 4 are 0. One and 4 are 0. Okay, number 2 is minus 20. Number 5 is minus 20. Take care of the sign. This one, what is it? Clockwise, so it is minus it is minus 33. And the other one is equals to minus of that. Alright. The corresponding equations are 10, 11, 13. I clear this off first. 10, 11, 10, 11, and then 13, 14. Okay, so I think we get all of them. We have the fixed end reactions, and we are going to address the external force. That includes the moment. So fixed end reactions, we collect it from all members. Done. The last one. Copy down. For external forces, we come back here. This DOF is number 9, 15 plus 15, and number here 11 minus 20. So the external forces minus fixed end reactions in global coordinates is going to be here minus here. Control Shift Enter. Okay, and now the displacement solution will be obtained in the following: U4, U5, well, I think we can copy down and we center it, and this is equal to mmult of m inverse of the system stiffness matrix multiplied by the externally applied loads minus the fixed end reaction. I hit Control Shift Enter. We have to come back here. I think the EI here is 8. This is 10. I haven't fixed all this. How about this one? This is supposed to be 6. Okay. This EI is 6 and the length is 3. And the first member 4 EI and the length L. Okay. So we fill in the values, which is now matching with the problem. Previously we haven't filled that in. Okay, so the displacement solution come out, and you can compare the result from this case with this case. I can just copy this and paste here. Okay, so U4 6344, U7 and U10 6344, 6344. I just take this. Okay, U6.76, U8 14. Okay, everything match. 47, 9 and 2 and 1.14. right? So the result you obtain from two solutions are identical, as long as everything is consistent. As I mentioned before, you'll be getting the identical displacement solution, and from this point you can calculate all reactions at the nodal point later from this step.